thanks, Simon, for being instrumental in this talk. So one of my collaborators on CHIME, who's an old radio astronomer, told me many years ago that there's nothing new in radio astronomy. I think he's half right. So hopefully during this talk, I'll convince you of the half that's true and the half that's not true. There are at least a few new things in radio astronomy occasionally. So this is a cosmology talk. So I have to give you the ubiquitous slide that's in every cosmology talk. So this is our version of the history of the universe. We know that it started off with a big bang about 14 billion years ago. We think it proceeded through a period of rapid expansion called inflation, less than a second after the Big Bang. After that, it kept expanding, but at a slightly more lackadaisical pace, cooling as it expanded. Eventually, the first nuclei and hydrogen formed. That caused the cosmic microwave background to be created and head towards us, which we see now with our CMB telescopes. After that, the first stars and things like that formed. And eventually, after about 4 billion years ago or so, that expansion of the universe began to accelerate. And then we head all the way to today, about 14 billion years after the Big Bang. So if you take a cosmologist, so this is our view, this is our history of the universe. Obviously, we know a whole lot about it. The model that describes this universe is something we call lambda CDM. Oh, right. There we go. What I'm going to focus on today is trying to answer the question of what's causing the acceleration of the expansion rate of the universe. So we attribute this acceleration as being due to something we call dark matter. We think that maybe the best model for it is a cosmological constant. So just a number we stick in general relativity that tells us there's some constant associated with space, and that's causing the acceleration of the universe. So this is the lambda in lambda CDM. CDM, of course, is cold dark matter. So the components of our universe are primarily dark energy, about 70% of it, and cold dark matter, about 20% more. So understanding the fundamental nature of dark energy, whether it's a cosmological constant or something else, is interesting. It's 70% of our total energy content. Sounds like a useful thing to try to understand. The story of what's going on with the expansion rate has gotten more interesting in the past 5 years or so. First of all, there's a now well-known tension between measurements of the cosmic microwave background and measurements of supernova. So if you ask CMB people, how fast do you think the universe is expanding today? We'll give you a number that's 67 in units of kilometers per second per megaparsec in H. And if you ask people who study supernova, how fast is the universe expanding today? And those people presumably know the answer because they're watching things move around. They'll tell you a different number entirely. It is, in fact, and both of us think that we understand our error bars well enough that the fact that we're getting different numbers is now important. So there's as much as a 4 sigma tension at this point between, almost 5 sigma tension now between measurements from supernova and predictions from the cosmic microwave background. So that could be telling us that something interesting is happening with the expansion of the universe or our fundamental model describing it. And more recently than that, in April, a measurement using a bunch of different galaxies also provided a kind of interesting tension. So if dark energy is a constant in these units of W naught, WA, don't worry about them too much, the cosmological constant, lambda, would just be this dark point right here in these units. And the measurements from these galaxy surveys are in tension with that, depending on which special combination of probes you're using between 2 and 4 sigma tension. So this measurement, WA, is an estimate for how much dark energy might be changing with time. So this is saying that these models, the data from these galaxy surveys, are starting to predict that that dark energy is changing with time instead of being just a constant. So that would lead us to think perhaps new models are going to be required. So we're not sure if dark energy is really due to a cosmological constant, if it's dynamical, if it's changing with time. We would have to start writing down new types of models, maybe those relying on scalar field theories or things like that. Of course, there's always the fundamental question underneath it all, is general relativity just wrong on large scales? So dark energy is an interesting thing to try to measure. We should try to do it, whether it's a constant or there's something else going on with its dynamics. It's really important to understand what's going on with the 70% of our energy in the universe. These tensions, I should note, they could be hinting at new physics. They could be hinting at the fact that we don't understand something about our systematics or something about some of the measurements. 2 to 4 sigma can go away when you get more statistics. So I don't want to say the only reason to ever try to measure dark energy is because of these tensions. They may be pointing to new models that we have to use, or they may eventually go away as we understand our instruments better, or somewhere in between. But either way, we would really like to understand what's going on. So the only way to really do that is, instead of asking how fast is the universe expanding today, how fast do we think it was expanding according to the cosmic microwave background, what we want is a measure of the expansion history of the universe. So how fast is the universe expanding with time? To do this, there's a fundamental scale that gets set when the universe is very young. We see this when we make a measurement of the cosmic microwave background. We take every hot spot or cold spot in the CMB and stack on it. We find this kind of curious ring-like feature around all of those hot spots or cold spots. It turns out, if you do the same type of thing with galaxies, so if I go figure out where all the galaxies are in the universe and I stack on every location of a galaxy, I also find an average signal that's a kind of ring-like feature around my stacked galaxy set. And these two rings, the cosmic microwave background from when the universe was about 400,000 years old, and the rings that we can see today and where all the galaxies ended up, have the same fundamental scale. This is how we are going to use this fundamental scale to understand the expansion history of the universe. But before I do that, I should at least tell you where this scale came from, so we understand why we think we can use it. So when the universe was very young, it was a coupled fluid, so right after the Big Bang, more or less. It was a coupled fluid of photons and baryons. All the particles were scattering off of each other. That universe had overdense regions here and there, seeded throughout the entire universe due to quantum fluctuations from before. Each of these overdense regions would seed a pressure wave that would propagate outwards away from this overdense region. So everywhere you have an overdensity, eventually it would pull in enough baryons to form a ring around it. Because the fluid is coupled, the photons and the baryons, so in this world, just imagine all the particles, would also expand outwards with this wave. So we're going to keep fast forwarding in time and watch this ring-like feature kind of propagate away from each of these overdense regions. So you fast forward a little bit more, the rings have gotten larger. And then as this is happening, the universe is cooling and expanding. And around 300,000 years after the Big Bang, the universe has cooled enough that now the electrons can get trapped into neutral hydrogen, and the photons that were being coupled in this fluid are now free to stream away from us. So we'll see them again as the cosmic microwave background. But the things that are left are a bunch of baryons that are living in the central overdense region and the ring-like features around it. So I'm going to do a top-down version of that. If I just take my frozen universe and I look down at where the overdensities are, I have all these like central overdensities and then ring-like features around them. If I fast forward billions of years later, because these central overdensities and the ring-like features around them have more baryons in them, I'm preferentially going to form galaxies there. So I'm going to get more galaxies in the center where I have more baryons, and then I'm also going to preferentially form galaxies and ring-like features around it. So we can measure that with galaxy surveys. So if I go and take a survey of galaxies and I measure where all of these galaxies are in the sky, then I ask, on average, how many galaxies are a particular distance away? So I say, okay, I'm interested in distances that are, whatever, the size of this green line. I'll put a little marker up for how many galaxies are exactly that distance away, and then do the same thing for every pair of galaxies I find in this map. So I'm going to build up a histogram of just distances on the sky between galaxies. And I'm going to find, when I do that I have a lot of galaxies that are close to each other. That's because I have those central overdense regions where a lot of the galaxies were formed next to each other. But I also find a remnant at a particular separation. This is the ring-like feature. So I also find a preferential separation at the distance of that ring between the center and the radius of the ring. This is known as the baryon acoustic oscillation peak. These ring-like features are baryon acoustic oscillations, and the presence of this peak is indicating that preferential scale for the ring-like features that were seeded from the very beginning of the universe. So this gives us one special scale in the universe that we can now measure at different times. So we know the fundamental scale from the cosmic microwave background. We get those measurements from the CMB, of course. And then we can measure this same ring-like feature at different distances and different redshifts and watch basically as this ring-like feature gets bigger and bigger. So we should see this peak change its location, change its distance away from the middle with time. So we're looking for that feature, and then we can use that to understand how it changes with time, and hence learn something about dark energy. Okay, so I should say this measurement, I'm not showing any data from it. This measurement has been done. So people have looked for these histograms with galaxy surveys and found them at many, many sigma significance at this point. So there's many galaxy surveys that are ongoing right now or two really great galaxy surveys that are ongoing right now. But it's worthwhile thinking, how could we make a measurement a little bit better than the current galaxy surveys can do? And that's because there's a slight limitation in the current galaxy surveys. So if I make a simulation of a bunch of galaxies, here's my central ring-like feature, and here are all of the galaxies in gray that are possible galaxies that live in these overdense regions. In red are the galaxies that are bright enough for a given galaxy survey to actually be able to measure. So a galaxy survey can only pick out these individual red galaxies, but there are many, many more galaxies out there to give us sensitivity to this ring-like feature. And as you go to higher and higher redshift, where galaxies are fainter and fainter, you get fewer and fewer of these galaxies. So you have worse statistics as you go to more distant redshifts. And that's usually where you're more interested in making this measurement. So that's sad for galaxy, for those of us who would love to measure large-scale structure. There may be an out, however. So if I imagine that these galaxies, if I just imagine that I made this measurement, but I averaged the emission of many galaxies together. So I have a low resolution telescope that averages emission from many, many galaxies together. I could still imagine picking out this ring-like feature that's going to tell me about dark energy, but I don't have to resolve all of the individual galaxies that went into that map. That's just because there are many galaxies that go into this ring-like feature. So if I can average the emission from all of them together, I could get a better signal-to-noise measurement of these ring-like features and thus dark energy. So nature has given us exactly what we would want to do to make this measurement. So all of these galaxies are bright and neutral hydrogen. Neutral hydrogen emits a 21 centimeter photon when the electron goes from spin aligned to spin anti-aligned. So these galaxies are all emitting 21 centimeter photons. And this is what we're going to use to make our measurement of all of these galaxies. So if I were interested in galaxies between a redshift of, say, 0.8 and 2.5, I, of course, won't build an instrument that works at 21 centimeters. I need something that looks at redshifted 21 centimeters. So if I was interested in galaxies at a redshift of 0.8, I would be, as the universe expands, that wavelength gets longer. So I would be interested in 37 centimeter photons for a redshift of 0.8. Similarly, for a higher redshift of 2.5, you get even more expansion. So my wavelength has shifted all the way up to 75 centimeters. So if I was going to build a telescope that would measure galaxies and dark energy between redshifts of 0.8 and 2.5, I would build a telescope sensitive to 37 to 75 centimeter photons, or 800 to 400 megahertz for people who think in frequency units. All right. So we built it. This is CHIME, the Canadian Hydrogen Intensity Mapping Experiment. It operates between 400 and 800 megahertz, so that gives us access to redshifts of 0.8 to 2.5. It is composed of 4 cylinders. Each cylinder is 20 meters wide by 100 meters long. So we have a total of 100 meters by 80 meters of collecting area. All told, that gives us about 1/4 of a degree or to 1/2 of a degree resolution on the sky. So this is a very, very low resolution telescope. No optical astronomers would be interested in this measurement at all. Most radio astronomers wouldn't be interested in this measurement at all. It is pure cosmology at this point. We have 1024 channels in that 400 to 800 megahertz range. So that gives us about 1,000 redshifts between redshift 0.8 and 2.5. And then instrumented on CHIME are over 1,000 dual polarization feeds. So it's over 2,000 channels that we're reading out, one for each polarization, with nice low noise. The cylindrical dish design, so you may notice this doesn't look like a regular telescope. The cylindrical dish design helps us map half of the sky every single day. So it's a very fast mapping experiment. All right. And then here's what we think we can do with CHIME. So the forecasted error bars are in orange. So we fill in this whole redshift range from 0.8 to 2.5. This is, of course, ideal. So if we have no problems at all ever in our instrument or anything else, these are the error bars we would project. Then we can compare that to the projections from the current best galaxy survey that's taking data right now, DESI. So they have access to the same redshift range. Their error bars get larger as you go to those higher redshifts because, as I said, they have less sensitivity to, they have fewer statistics because they have fewer galaxies out there. So I should have said what the units are, sorry. On the x-axis is redshift, so that's giving us access to redshifts 0.8 to 2.5. The y-axis here is more or less the cosmological volume that we're probing. Here, if dark energy is a cosmological constant, all of our data would line up along 1. We've divided it by our fiducial cosmological model. So if dark energy were a constant, we would just find all of our numbers basically scatter along a line of about 1. CHIME has been acquiring data for almost 6 years now. So we began acquiring cosmology data on October 7th, 2018. We had our first light ceremony the year before. So this is the Canadian Minister of Science. This was a big deal in Canada. So there was a whole ceremony for it. You can kind of get a sense of the scale of CHIME. So obviously this is a person, and this is one of our struts from one of our cylinders. So it is a very, very large instrument. Okay, so we have many years of data in the can. What do we do with it? Obviously, we immediately constrain dark energy. So we just type in our 5 lines of Python and then write a paper about how we've constrained dark energy. Not exactly. So the first thing we should do, because nothing like CHIME has ever existed before, no one's built this type of instrument, no one's tried to do this type of science before, we are lucky that we are trying to measure galaxies. And so if we already have a galaxy survey that someone hands us, we know that we think there's neutral hydrogen in those galaxies, otherwise we wouldn't have bothered to build CHIME. So the first thing we should probably do is correlate with galaxy surveys. So that is in fact the first thing we did. So we have 2 papers out. The first results papers out. The first one is a detection of cosmological 21 centimeter emission with CHIME. So this was officially accepted in 2023. So what we did here was basically take the best galaxy survey that we had. Everywhere there was a galaxy from that catalog, we stacked our CHIME data set on it. So we stacked the emission from many, many galaxies together to find a positive correlation with galaxies. So that means there's neutral hydrogen out there. Neutral hydrogen lives in galaxies. That's great. CHIME wasn't a crazy thing to build after all. Fantastic. I should note Simon did a lot of awesome simulation work to help us understand some cosmological constraints from this. This paper was a magnum opus of many different analysis techniques and simulation results and parameter constraints. Our second results paper was a detection of cosmological 21 centimeter emission from CHIME in cross correlation with EBOS measurements of the Lyman alpha forest. So this is a little bit different. If you have a quasar that's at high redshift, so a really, really far away bright thing in the sky, as the light from this quasar goes through the universe, anywhere there's a cold cloud of neutral hydrogen, that light will get absorbed. And so there are absorption lines along the line of sight from us to the quasar, and they're up to 100 sometimes per quasar. So, so we could do the same thing. We knew where all of these absorbers were, be from this exact same catalog, more or less. So we can take the CHIME data, anywhere we thought there should be an absorber, we pick out our little data map voxel pixel and stack on it. And we found an anti-correlation between the galaxy data set and the CHIME data. That's exactly what you would expect for an absorber. So we should expect no neutral hydrogen emission from an absorber. So the anti-correlation was a good sign that our analysis was not crazy and we were doing something right after all. So we have 2 results papers out. They came out last year. What I'm going to say next is basically a crime of humanity. That's the most I'm going to talk about CHIME results in this talk. So normally I would now proceed to discuss all of our results papers in way more detail. I'm not doing that. And that's because I want to talk about what we're going to do next with CHIME. So we came here for the dark energy. At least I joined CHIME to help constrain dark energy. These results, you may notice, neither of the titles of those papers were CHIME constraint on dark energy and its dynamic whatever, right? So we didn't detect dark energy with our cross correlations. That's fine, but we should understand what we need to do to make it to the next step and actually constrain dark energy with CHIME. So this is hard for the following very important reason that some of you may be familiar with. If I take a map, this is a CHIME map of the sky. It's in the middle of our band, so a bit above the middle of our band, 680 megahertz. So this is an actual map of the sky. So this is right ascension and declination, basic kind of east, west, north, south. So the entire sky that CHIME sees every day. We make one of these maps at each of our frequencies every single day, stack it together and make a full data set. So you may notice that this map does not look like a bunch of galaxies on the sky, right? I showed you the artist's depiction of what a galaxy survey looks like. It's a bunch of little point sources all over the place. That's not what this map looks like. The major emission in this map is in fact from our own galaxy. That's this thing that goes down here, comes back up. The galaxy in these units I promise I'm not going to tell you about is 40. And our signal, the distant galaxies that are emitting in 21 centimeter, it's down here, 5 orders of magnitude smaller. This is a linear scale, so to first order, it's just 0, basically. So the galaxy, our own Milky Way galaxy, is incredibly bright in synchrotron emission. As I said, 5 orders of magnitude or so brighter than our signal that we're interested in. So this is our biggest problem in CHIME, is trying to see through this incredibly bright foreground emission. We have hope that this is possible. So I should point out why we've known about synchrotron emission from the galaxy for a very long time, so we knew that this would be a problem. You should then wonder why we were so crazy to build CHIME in the first place. And that's because we think that we can remove it. So that works the following way. If I take this is a simulation now, not an actual map of the sky, but if I take a simulation of our unpolarized sky, so just how bright the sky is in different places, I'm going to take a little slice right here through the middle of our galaxy, so kind of one of the worst offender regions. And then I'm going to blow it up as a function of frequency. So here's my slice in degrees, and then here's what that emission looks like as a function of frequency. And I'll just focus on a random 100 megahertz part of my band, so about a quarter of our band. So if I look at that slice as a function of frequency, I notice that it's very smooth. It's incredibly bright in these other totally different units. It's 750 Kelvin, but it's very smooth. If I know what it is at one frequency, I can pretty much predict what it's going to be at some other frequency. My signal, on the other hand, shown over on the right-hand side, is very different. If I take the same slice of sky, so again, same deal, this is slice, and then I'm going to blow it up in the same frequency range. Now my signal looks very different. And that's because I have a bunch of galaxies at one redshift, which for this is one frequency. At some other frequency, they're totally different galaxies at a totally different redshift. So it's a totally different universe. So I don't have any correlation. I don't have any similarity between galaxies at one frequency and galaxies at some other frequency. So my signal is Gaussian, more or less, in frequency. So I have a nice smooth foreground and a bunch of ripply stuff that's my actual signal. So I can obviously just remove a smooth thing from the combined map of these two things, pick out the ripply stuff, and move on with my life, constrain dark energy, and we're obviously done. And then again, here's that difference in order of magnitudes in these units, 750. So it's a 6 order of magnitude or so difference between these two. Okay, there is, so the reason we still don't have a dark energy constraint is that it's a bit more complicated than that. And that is, in order to actually do this difference between our signal and the smooth foreground, we need to understand our instrument very well. The main one I'm going to focus on is how to understand our beam. So we need to understand our beam to about 0.1% to be able to make this measurement. Okay, so you're probably wondering, what is a beam and why does it screw up our measurements so badly? So if I take a very simple beam from, say, a nice round telescope, it'll have a kind of airy pattern. So it'll have a Gaussian inner beam and then some side lobe structure on the sides. It nearly trivially expands with wavelength. So it's wider at 400 megahertz, narrower at 800 megahertz. And if I imagine measuring a bright source directly overhead this beam shape, I will measure my signal at 400 megahertz in some units, and maybe a slightly brighter signal at 800 megahertz. And this band pass is basically just however good and smooth my amplifiers are. Maybe my amplifiers are a little better at 800 megahertz. Maybe my telescope gain is better there, et cetera. So with a source overhead, I'll just measure the gain of my instrument, and that's fine. If that source moves a little bit away from being directly overhead, I'll measure it at maybe half power at 400 megahertz. Maybe I measure it in a dip at 600 megahertz, and then I get another peak at 800 megahertz. So this is bad. That's because I now have injected a frequency dependence into my foreground. If I imagine this is my foreground source, I now have a dim, very dim, bright thing as I go down in frequency. So I've injected a ripple into my frequency dependence that mimics my signal I'm interested in. So this means I can no longer do my simple differencing of a smooth thing because my foregrounds have a frequency dependence that they didn't have before. So I'm imparting a frequency dependence because I haven't understood how to remove my beam, my instrument beam. If I knew this beam shape, I could take it into account, and then I wouldn't have this problem anymore. So this is what drives our requirement to understand how our instrument sees the sky, because anything we don't understand will get multiplied by that enormous foreground emission, and we won't be able to remove it from our signal. All right. So what is Chime's beam, and how are we trying to measure it? So this is the best case scenario for Chime's beam shape. So those cylindrical reflectors is kind of the beam envelope from a cylindrical reflector. If I took a single detector and put it on one cylinder, I would measure a beam shape that extends all the way from north to south. That's because I have no curvature for my dishes. So I have total access from north to south, from the north to south of the beam. And then I have a little bit of curvature in the east-west direction, so I get a curved beam east-west. So that's shown up here. This is north to south, so this is my hot dog shape in the sky, and then a couple degrees wide east-west. So I am measuring a hot dog in the sky. In these particular units, there's a discontinuity at the pole. Don't worry about that. You should just imagine the beam shape from Chime is a hot dog in the sky. That was on purpose. And that's because this is what gives us access to half of the sky every day. So as the sky rotates overhead from east to west, we map out the entire sky every single day. All right, so this beam shape is great for building a fast survey. It is, however, very challenging to calibrate. So first, it's shaped weird, so that's unfortunate. But also, as a point source transits through CHIME, we measure the flux from that point source, but we also measure the flux from the whole radio sky behind it. So we have what's called poor point source resolution. So we can't measure point sources particularly well. So that means the usual way that a radio astronomer would calibrate a telescope doesn't work anymore. Usually you pick a bright point source, you kind of scan over it, something like that. We don't do any of that. CHIME doesn't scan, it's way too big. And our point source resolution is poor, so we don't really see that point source anyway. So this makes it challenging, to say the least, to calibrate. And it gets worse. So we can measure point sources right when they're directly on transit. So as the sky rotates from east to west, point sources are transiting all the time. We can, right when they're directly overhead, we can figure out how bright they are and use that to try to estimate our beam shape along the hot dog region of the beam. So from the north to south. So right when they transit, we can kind of measure the shape north to south. This is an actual measurement from measuring all of the point sources that we could find in a catalog. This was the beam shape that was used in our results paper. And you notice that it's not smooth. It has these ripply features. That's from reflections and other mutual coupling along the cylinders. So we have populated CHIME with a bunch of feeds along each of these focal lines. Those feeds talk to each other. Signals rattle around up and down and reflect from the focal line down to the feed, down to the focus and back again. So we form interference fringes basically in our north-south direction from doing all of that coupling. So our beam is complicated in the north-south direction, to say the least, but hey, we measured it. So pat on the back, doing a great job. But wouldn't we love to also know our beam in the east-west direction? So what we're showing here is just basically take a smooth Gaussian thing and then assume that's our east-west direction. We'd love to know if that's actually true. One of the sources in the sky that evades our sources are too dim to see them away from the transit location is the sun. The sun is very bright. I don't know if you've noticed that in Arizona, but it is. So the sun also happens to move from the north to the south during the course of a year. It moves from -23 to +23 declination. So we have a measurement in the southern portion of our beam from a year when the sun was at solar minimum, so it was not particularly variable. That measurement was written up in this paper and is shown on the right-hand side in, of course, completely different units. Sorry about that. These units are chosen to make the beam shape. Basically, imagine we've just asked, what is the beam shape as I stare down at CHIME? It looks like this. So things are nicely orthogonal in a way they wouldn't be in a sky projection. So this is a measurement of our beam shape from the sun. So again, here's the meridian, here's the transit right overhead where CHIME is mostly focused. But you see there's all this structure and all this power away from the main beam at order 10% or so of the total amplitude of the main beam shape. So it's a significant power actually for CHIME. If we want to understand our beam to 0.1%, anything that's as bright as 10%, we better know about. And has all this has all these fun features. So instead of being this nice, smooth Gaussian shape, it has all of these features in the east-west direction as well. So now you might start to worry because we have a lot of structure, both in the north-south and in the east-west direction. So far, I've only shown you a tiny fraction of our total beam, right? I've shown you a slice on the north-south and then a little bit of the southern beam shape. So wouldn't it be great if we had some other way of also understanding our beam, maybe in the places where the sun doesn't go? So this is where holography comes in. So this is a measurement that I started as a postdoc in Toronto. So I built a receiver that went on the focus of a steerable dish that's near CHIME. So this is the Gault 26-meter telescope. Chime didn't exist yet, I think, when this picture was taken, but it would be out in the field over there. The signals from this telescope go down a set of amplifiers and a bunch of coax and over into the chime correlator. So chime is an interferometer. That means we correlate every feed on chime with every other feed on chime. That's how we get additional resolution between our telescope reflectors. So our two signals from the Gault telescope are added into the correlator, and the signal from that telescope is correlated with every single feed that's on chime. All right. What do we do once we've built this instrument and put it on? We use the Gault telescope to track sources as they transit through chime's beam. So the Gault telescope, because it is not a cylinder and it is a nice round telescope, doesn't have this whole hot dog shaped beam on the sky. It's just a nice round beam. So as the Gault telescope tracks a point source, the correlated signal, the correlated signal between the Gault telescope and chime measures only what's common between the 26-meter and chime. So we zoom in on just the point source itself. All of the other stuff in the sky doesn't end up in the correlation because it's not anywhere in the Gault telescope's data. So we really zoom in on point sources, and that allows us to have additional sensitivity in the east-west direction that chime itself doesn't have. So this is an example of holography data. So this is a paper published by my graduate student, Alex Rita. So it gives you quite a lot of information. I'm going to go really slowly through these panels. Chime has two polarizations. I measured dual pole feeds. So we measure east-west polarization. So each feed on chime has two polarizations, one in the east-west direction, kind of along this 20-meter direction, and one in the north-south direction, so along the cylinder itself. The Gault telescope also has both linear polarizations. Right when the Gault telescope is looking up as a source transits, those polarizations are aligned. So the Gault telescope has an X and a Y polarization that's exactly the same as chime right when it's looking overhead, right when it's looking up. So this is an example of a copole amplitude. So this is when we're measuring the same polarization between the Gault and chime. So you see this now familiar inner beam shape, Gaussian profile. And then there's signal power all the way out, even beyond what's shown here. With good signal to noise, there are actually noise estimates on here in little gray bands. So all of these ripple structures and all of that stuff, that's all real. That's all actual chime beam shape. You can zoom in on the narrow, on an inner region of our main beam. The different colors are averages across the 4 different cylinders. You can see they're fairly similar. There's a little bit of a pointing offset between the cylinders, but they're, they have the same rough shape and approximate location for the side lobes. This is one of the powers of one great thing about holography measurements. Because we correlate every single chime feed, we have a measurement of the beam pattern of every single feed on chime. So if feed-to-feed variations are important in the chime beam shape, this is one of the only ways we would know how to estimate what that effect is. So we can play around with how to combine the holographic beam shapes to estimate effects of if one feed is a little different from the other feed, what's the overall impact on our cosmology. We also measure phase. This is really important for combining all of the holographic measurements together to form what is the actual chime beam. So we have a bunch of copole stuff where we're measuring the same polarization. We also get cross-pole amplitudes. So again, there's a sort of a north-south polarization and an east-west polarization. We can measure the cross-pole, what's being picked up by chime's X polarization that's actually living in Y. So this is cross-pole. Here, there's a dip in the middle because when you have two polarizations looking at exactly the same thing, they should be minimal because you should have no signal power. Polarization should be orthogonal is another way of putting that. So this is a pretty classic cross-pole beam amplitude shape where you have a dip in the middle and then peaks on each side. Again, error bars are shown. So there are actual errors on all of these measurements. These cross-pole values are real. So this is real chime cross-pole amplitude. All right. So of course, that means we can compare these measurements where we have overlaps. So this is a sort of cartoon of where we have holography data. So again, we have north-south data from all of the point sources that transit through CHIME that tell us all of the ripply reflective structure along the north-south direction. We have solar data in the south, and then we have six sources that are published in that paper. We actually have 20 sources we've measured total. 4 of those sources overlap with the sun. So I'm going to show on the right-hand side a comparison of those data sets. So each of these panels is a different source presented in that paper. The top 2 do not have any solar data, so holography is shown in color, and the sun is shown as black lines. So these 4 sources overlap between both the sun and the holography measurements. This is a single polarization, single polarization, single frequency. So you can see a couple things. One, generally the beam shapes match between holography and the sun. That's good. There are some places where holography seems to dip lower than the solar measurements. We think this is due to improved signal to noise. So we just have better signal to noise in the holography measurements. So we can measure these lower signals a little bit better further away from the chime beam shape. The inner beam, sort of this main beam feature, is not as well captured. So it's a little broader in the solar data set than it is in the holographic data set. I'm going to expand on that in what's next. So a particularly egregious example of where solar data and holography data disagree is this panel right here. So this is tau A. This is one of those 5 sources. The black line, again, is solar data, and the blue line is holography. And these 2 are different polarizations. So in YY, the one aligned with the north-south direction, the solar and holography data agree fairly well. So they pretty much match each other. For XX, however, that is not true. So we see that the holography data has this kind of nice Gaussian inner beam, kind of what we've been used to, what I've been telling you all about for the past however many minutes. Whereas the solar data has a kind of dip in the middle and some peaks on each side and is much, much broader than the holography data. So these discrepancies between solar data and holography data are at some frequencies. The top of our band, so 750 to 800 megahertz, that's the top 50 megahertz of our band. At some declination, so again, shown here, some locations in the sky. So again, this is tau A, and really in only one polarization. So it really only ever shows up in the XX polarization. All right, it's quiz time. Does anyone recognize a shape that has a dip in the middle and 2 points on the side from like 2 slides ago? Cross pole. Yeah, you got it. Okay, so look, if we go back, there's a thing that has a dip in the middle and 2 peaks on the side that's cross pole. So that's a hint as to what's actually going on here. If we try to use both copole and cross pole, and in fact, every combination of holography data you can get for this transit, we can reconstruct using a full combination of co and cross pole. We can reconstruct what the chime beam shape should actually be. So if we add the cross pole back in, we find that we can reconstruct the chime beam shape. So we reconstruct this double bump in the chime data using the full polarization information from holography. This is actually evidence for polarization leakage in chime. So we wouldn't have known this if we didn't have access to these holographic data sets. We wouldn't have known that the real problem here was that there's additional cross-pole leakage at particular frequencies and locations on the sky. Where this fundamentally comes from, we do not know. So that's TBD, trying to figure out what in our optics, what in our modeling is actually could account for this. But for sure in the data, there's additional cross-pole leakage that we didn't expect. Okay. You should check out Alex's paper. It's great and has a ton of information about all of the many more things about holography. The measurements are fantastic. I'm going to spend my last 2 minutes thinking even further into the future about how we might be able to measure the beam shape of chime with, for example, drones. So we undertook a beam calibration or a beam measurement campaign with a drone. So here's our drone. It's hovering near chime. The idea is actually pretty straightforward. You transmit a signal from the drone as it flies over chime. Chime measures how bright things are as a function of time. You match up where the drone was with how bright chime saw it, and you made a beam map. So it's pretty much that straightforward. And there are no other problems for making this measurement. So for the measurement we presented in this paper, we flew just an east-west trajectory. So here's chime with the 4 cylinders. We took data from a single cylinder. We flew about 220 meters south of the edge of chime in just a straight line from east to west. So we are just making one single slice measurement of the chime beam shape. The main goal for this campaign was actually to understand whether we could even in principle measure anything about chime with a drone. That's because we flash the signal on and off. So we want to have a lot of on and off measurements. And chime's integration period is 10 seconds. So if we wanted to measure an on and an off, or say 5 ons and 5 offs of our telescope, we need to hover the drone for about 50 seconds to get 5 periods where it's on, and about 50 more seconds to get 5 periods where it's off, and then move the drone over. So that's hovering for about 2 minutes over every point you'd ever want to measure on chime. That's a very long time. I don't know if I told you this, but chime is 20 meters by 100 meters. So if you're taking 2 minutes for every point along chime, that's like decades of making this measurement. So we can't do that. What we did instead was implement chime's gating mode. So chime measures pulsars. We were able to zoom in on our source as though it were a pulsar and gate on it. So this allowed us to make a much faster measurement of chime. I'm happy to talk even more about it if people are interested. So when we fly from east to west on chime, we measure a projection that's a kind of a little bit of a north-south projection on the sky. So we get a little bit of north-south coverage as long as we believe every feed on chime is identical. So I'm not going to go into any more detail than this really about this paper, but I wanted to flash one thing that I'm really proud of from this measurement. So on the left-hand side is our measurements from the sun. So this is in basically east-west, north-south units. So the chime beam, you know, has a big bright center, and then you see these side lobe regions off on the sides. So this is in the XX polarization and the YY polarization. Point out a few things. One is that the side lobes kind of curve away from the main beam in XX, whereas in YY, they're basically orthogonal. Same thing, you get kind of these hatched patterns in the YY. So the drone measurements, which again, this was just to prove that we could measure anything from chime. We weren't really trying to measure its beam pattern at all, but we actually picked up some of the same structure with the drone. So here again, you know, in the solar data, these side lobes are sort of orthogonal. We pick out the same thing from the drone. You get these side lobes that are orthogonal to each other, whereas in the XX, you're starting to see them curve away. So I think this was a really great demonstration. We're excited to go back to chime and make more measurements in the next sort of 6 months or so to really begin mapping the beam shape with the drone. Wait, so in summary, there are many papers that we've published that have a lot more detail on everything that I've said. So holographic measurements, R2 detection papers, so they're magnum opus of 120 or something pages total between the two of them. So there's tons of information about how we actually extracted cosmology, or at least some parameter constraints from our detections with chime. We have an overview paper, so if you want to know all about how chime was built and what's on it, there's an overview paper describing the instrument, and then the solar measurements that I also discussed a lot for measuring the beam shape. More results are imminent. We have galactic science, so one person's foreground is someone else's science, and GRB monitoring, et cetera. There is, of course, a ton more work to do. So we need to integrate and use the data that we have from our beam models and actually use them in our cosmological pipeline. briefly mentioned, the beam model that we're using in our two results papers is very naive compared to how much information we actually have about the beam. So we know a lot more now than we did when we published these papers. We need to incorporate that into the pipelines and get that through. So we also have to do more modeling and improving our data filtering so that we can get down to our interesting dark energy science. Thank you.